Okay, so I'm pretty much going to start off where the previous talk. I should turn this on. Cool. Is it recording?
Yes, it is.
Excellent.
Could you clap for for synchronization
I'll
purposes?
tap in a minute.
Okay.
Okay, so I'm pretty much going to begin where the previous talk left off. So far we've proven Cauchy for triangles, which gave us convex Cauchy, and from that we get loads of beautiful results like Liouville's theorem, the fact that holomorphic functions equals power series, everything's infinitely differentiable, and so I'm gonna hello, you missed nothing. So this chapter is going to be studying singularities. So kind of what is a singularity and how should we think about them? What's really going on there? So first I wanted to kind of recap on a really high level why we care about things like Cauchy's theorem. And then I'm going to prove general Cauchy for simply connected domains. So the reason we care about things like Cauchy's theorem is we're studying whether a holomorphic function has an antiderivative. And the reason contour integrals are so nice is that if we have an antiderivative, then the integral is path independent by the fundamental theorem of calculus. And if the integral is path independent, then we can construct an antiderivative by just defining our antiderivative as the integral along a path from a particular fixed point and our endpoint. And as hopefully we've seen in the course, if we define something like this, we get an antiderivative. So this is equivalent. And being path independent is the same as saying that if I have two paths between any two fixed points, the difference between the integral is the same, which means that the integral around the loop is 0, and Cauchy's theorem is all about when integral around loops are 0. And so the reason we care about things like Cauchy's theorem is that they tell us knowing the integral around a closed curve is 0 tells us there is an antiderivative, and vice versa. So we already know that, so fact, convex Cauchy, i.e. if we have a function which is holomorphic and has a convex domain, then it has an antiderivative. This is important because it tells us that if we ever have a convex set and we have an integral along a path within that convex set, we can change that path to anything else which have the same endpoints, and the integral is the same. So, hello, you've missed nothing. You've missed nothing, it's fine. And so I'm now going to prove Cauchy's in general for simply connected domains. And this is kind of the key lemma we need to prove that, because this tells us that if we have a simply connected domain like this, and we have two paths within here. On a really high level, what this proof is telling us is that if I kind of cover this domain in convex sets, like this, and this, and this, pretend this is covering, then as long as I can break down my path deformation into a bunch of finite steps where each one happens within a convex set, it's allowed. Because we know that in a convex set we have an antiderivative. And by the fundamental theorem of calculus, if we have an antiderivative, the integral doesn't depend on the path we're taking. So I can, so the integral doesn't depend on the path I'm taking. So I can say that the integral along this path is the same as the integral along this path, which is the same as the integral along this path, which is the same as the integral along this path. So everything that follows, we're just kind of formalizing this key idea. And it's very important to note that this is strictly a topological fact. It doesn't, all of the interactions with convex analysis happens during convex Cauchys. Everything I'm about to prove is basically just saying, if I have two paths, and I can deform one to the other, then I can break this deformation down into finite many steps, where each step is contained within the disk. Raise your hand if you haven't done Metantop. Cool. Yeah. In that case, you might not follow some of the things that are going to happen next, but don't worry. I will say when all the topology ends, and you can resume paying attention. And I'm going to try and explain things where they make sense. Okay. So we're now going to prove simply connected Cauchys. And as I've just explained, we have like two paths, and we can deform one path to the other. And I'm trying to prove that I can break this deformation down into finite many steps, where each step happens within a disk, or some convex set, but they're going to turn out to be disks because disks are nice. And okay, so first a note on formalization. What does it actually mean to be able to deform one path to the other? So what it means is that I can kind of have a family of paths, like this one is my starting path, then after a little bit I have this, and then this, and then this, until I eventually get to my end path. But we're dealing with kind of topological ideas here. We don't want to have sequences. And so the way we deal with this is by having a function from the unit interval into the space of paths. And this is kind of icky and hard to work with. So I'm going to think about this as a function from the unit square into my space, where I kind of just draw a square, and I say that each vertical line corresponds to a unit interval, and that unit interval corresponds to a path. And this side, so label these paths gamma 1 and gamma 2. Then on this side, the path is gamma 1. On this side, the path is gamma 2. And as I move my vertical line across, the corresponding path I get kind of smoothly moves from gamma 1 onto gamma 2. So, and with the additional condition that this line maps to the start point, A, and this point maps to B. This is kind of, I think the point is not to get hung up on the details here, but we need to have a formal language to speak in for everything that follows to make sense. This is just kind of formalizing the idea that, like, I can smoothly change this path to the other and nothing goes wrong. So, okay, and now, the really key fact to observe is that this is a unit square, and the unit square is a closed and bounded set in the reals, and thus it is compact. And as people hopefully have a vague recollection of from Mess and Top, compactness is a really important and really powerful property, and in pretty much everything that follows, we're just going to be using compactness to get nice things to happen. So, okay, I'll write it here so I can draw anything out. So, okay, so this is all happening within some kind of simply connected domain. I'm going to redraw my paths so it's kind of more obvious why this is different from the convex case. Okay, so the first thing to observe, this is a compact set. This is a continuous function, and so the image of compact sets on a continuous function are always compact. And what's the image of this square? The image is just the area between my two curves. So the area between my two curves is compact. And in what follows, I want to be able to kind of create some compact sets to do my deformation inside. And the easy way to make a convex set is to say, I can draw a circular radius epsilon. And at each point in here, I can define a kind of max distance to the boundary function, like just what's the size of the largest disk I'm allowed to draw around this. And I'm not going to get into details of how to formalize this, but you can. The important thing to observe is that the kind of how big a disk, what is the radius of the biggest disk I can draw function is continuous. Because if I have 2 points really close together, and I can draw a disk around one, I can draw an almost the same size disk around the next point, just within the disk around the first one. And so this kind of weird function called what is the maximum distance to my boundary is continuous. And we know that all continuous functions on compact sets have a global minimum they attain. And so the reason for all this is that I can now write down there exists an epsilon such that for all z in kind of this shaded region, like call this region x, then for all z inside my shaded region, the disk of radius epsilon is within my domain. And, like, again, I don't want to get bogged down in formal details. The point of all this is that if I pick any point in the image of the square, like any point I care about when deforming a path, and I take a deformation where nothing moves more than epsilon away from that point, this is allowed because it's in a convex set, because things within distance epsilon of z are inside the set where my function is defined. And now, okay, so I've just got a statement about distance in the image. I need to convert this to a statement about distance in the unit square where I started with. And this is really easy to do, because my deformation is a continuous function from a compact set, and so it's uniformly continuous, which is a fact people hopefully remember from analysis too. And being uniformly continuous means if I have 2 points that are like, means for any kind of distance to move in the output, if I have 2 points that are at most delta apart in the input, their output will be at most some distance apart in the output. Or, sorry, I got a bit confused, so I'll write that form. For any epsilon, there exists a delta such that, like, for any points in the unit square, the distance between their outputs in the complex plane is at most epsilon. And what this means is that if I draw, say, like a square here, where the diagonal has distance at most epsilon, at most delta, then as long as my deformation remains within this square, everything in the output is within epsilon of where this point goes to. And so this means that I'm allowed to, I can now, let's just say delta is 1, because that makes my life easier.
You didn't write that delta.
Sorry?
X minus 1 as the delta.
Sure. So the reason this is all important is that now, in this square, I can, supposing delta is 1, so that I can draw squares like this, I can now look at deformations within here, and as long as each deformation is small, i.e. it only happens within one of these squares, then the deformation happens within a convex set over here, it is allowed. And I can just do this. I start with this line, I take deformation 1, like this, I take deformation 2, like this, I take deformation 3, like this, I take deformation 4, like this. And the path I get is just gamma 2, because it's the same along the bottom and the same along the top. So that got a bit more bogged down in details than I wanted it to, but we're really just proving a topological fact. If you can deform one path to the other, you can do this in finite many steps where you set happen on the disk. Does that all make sense to people? Cool. Should I speed up the pace at all? Cool. Yeah, I can't read the audience on that. Got some nods, got some shakes. So why, the natural question now is, I proved something connected to Cauchy's. Why is this an interesting result? So the first reason this is an interesting result is that we've just shown that if I ever have a space that's simply connected, i.e. it has no holes inside it, then any holomorphic function with that as a domain has an antiderivative. Like, this is a really cool fact, and it's really not always this is true. From a more utilitarian perspective, the reason this is really useful is it tells me that if I'm ever integrating along a path, and I care about this integral, like say I'm an applied mathematician and I'm trying to do a contour integral, I can just deform this path to anything that would be more convenient, and the integral is going to be the same. So, for example, if I wanted to prove Cauchy's integral formula, my life has now become much easier. I want to integrate f of z over z minus a, and rather than faffing about with all of the stuff we did in the original proof, I can just draw a big circle, there's an a over here, my path is around the circle, I can now deform it to a path that goes down, takes a tiny circle around here, and goes back up, like I'm taking a keyhole contour, and all of the deformations I'm making are within a simply connected set, so this is all fine. I have to, if I take a keyhole contour, I don't go through this line, then everything I've done is completely valid. And it's now a pretty easy exercise in formalization to show that these lines cancel, and the integral around this tiny circle is exactly what I want it to be, because my function is continuous there. So the real reason we wanted to prove this is that it's really useful for a theorem about to prove to show that the Laurent series exists. So let's just get on to that. So now I'm going to talk about singularities proper. So a singularity is a function which is holomorphic on some punctured disk, i.e. a disk that does not contain the center. And these turn out to be a really interesting object to study. And the motto I'm going to try and drive home throughout this talk is that it's not that the fact that my function isn't defined at the center of this disk doesn't necessarily, we can make much stronger statements than just it's not defined at the center of this disk. Because holomorphic functions are so nice, there's also a deep structure that emerges. So first off, I want to kind of port over my useful tools for studying these functions. So my most useful tool for studying holomorphic functions was Taylor series. And let's see if I can get a similar tool here, which we know are going to be the Laurent series. So just to draw on what this looks like, I've got some disk, I've got a hole at the center, the disk has radius r. And I now want to just repeat the proof I used for Cauchy's integral formula, or rather to prove power series, which was the proof of Cauchy's integral formula. I want to see where things break. So the magic function I used for Cauchy's integral formula was f of, I'm going to use a in here, so I'll just make my singularity be at 0 to avoid anything annoying happening. To avoid notational issues. This is just translation, so this doesn't matter, but it'll make my life easier notation-wise later on. So the point of Cauchy's integral formula, or the point of the proof, is that the fact that f is holomorphic means that this function can also, this function is holomorphic everywhere but a single point A. and is continuous at that point A. And I don't really want to go into the details, but all of the proofs we've done for Cauchy's theorem up to now still work for functions that are holomorphic almost everywhere and continuous to the points. As we'll later see, this is because they're removable singularities, which are just still holomorphic at that point. But you don't have to assume that. The proofs still work. So let's now think about what happens. So we start off by trying to repeat the proof of Cauchy's integral. We take some big circle, pretend this is a circle, and yeah, we take some big circle and we try to take the integral around it, and we want to say the integral of a holomorphic function around this is 0. Sadly, this doesn't quite work because there's a hole in the middle, and we know that when there are holes, our theorems don't apply. But what we can do is take our curve and deform it downwards. This is not the same. Well, this isn't obviously an application of the general Cauchy theorem we proved earlier, but you can show with not too much work that if you have some closed curve and you've got another closed curve and you want to show the integrals are equal, then you can just take this curve, deform it down via some kind of keyhole approach to this curve, and get that the integral on these lines cancel. Are people willing to just accept this is true? Cool. So we can now do that here. We take our curve, we deform it down to some much smaller circle, and we now know that the integral of g around these two curves is the same. And the key factor of everything that follows is going to be that on this one, the absolute value z is less than a. On this one, the absolute value is greater than a. So we now have this fact. And the idea of Laurent series basically immediately follows from this equation. Sorry, is it clear how I got this equation? This is just this is the same as the integral of g of z around gamma 1, because I can just split the terms in two. And this is the integral of g of z around gamma 2.
Sorry, are those less than or equal to signs? Sorry, less than signs.
Oh, no.
Yeah.
Those are minus signs. Sorry. People okay with this? Cool. And I can now just analyze these in pretty much the same way I did for proving power series. So these two terms are boring. On gamma 1, z is bigger than a, and as I proved last time, that means that this integral is just 2 pi I times f of a, because f of a is a constant. And this integral is just 0, because if you integrate 1 over z minus a on a domain that doesn't include a, then there are no holes inside it. And the integral around a closed curve when there are no holes inside is always 0. So this is just 0. And these now are the interesting terms. So on this, I can apply the same trick I did with power series. So because z is bigger than a, I want to write the denominator in terms of a over z. And I can now expand this as a power series. Etc. I'm just using the fact that 1 over 1 minus a of z is 1 plus a of z plus a squared over z squared, etc. And I can now switch the order of summation and integration. The reason I can do this formally is that this is a power series, and the ratio is strictly less than 1, and so it's a uniformly convergent series. And we showed in analysis 2 that we could always swap the order when this happens. Don't worry about the details if you didn't do analysis 2, but that is a thing we're allowed to do. And so this is now equal to like something times f of z over z plus something times a plus something times a squared dot dot dot. And this is just a power series from n equals 0 to infinity of some constants times a to the n. And we now just do the same thing to this, but now because a is always bigger than z, I'm going to take z over a as my term to kind of expand in terms of the power series. And this is the kind of weird funkiness that gives us the negative terms of the Laurent series. So that was how we dealt with this term. The way we deal with this term is we just kind of do the same thing. We now want to expand it as z over a and what we now get is f of z over a plus f of z over a squared plus dot dot dot. And we just repeat the same thing we did down here. This is uniformly convergent because the ratio is less than 1. We can swap the order of summation integration, and this is the sum from minus infinity to minus 1 of an times some constants. And I now just rearrange this equation, and I have a Laurent series. So I think the important thing to take away from this is not kind of all of the details of algebra I just went through, but that we just repeat the proof of Cauchy's integral formula. We can't quite do it because there's a hole in the middle, but we can deform our curve down to a smaller curve. And on the larger curve, we expand as a power series in terms of a over z. On the smaller curve, we expand as a power series in terms of z over a. And we just rearrange, and we have a Laurent series. So okay, so the reason we did all that is that we want to study singularities. And as with normal holomorphic functions, where power series were a really useful tool, here, Laurent series are a really useful tool. We can't quite port over our intuition for how power series works, but we can almost port it over, because a Laurent series is just kind of two Taylor series stuck together. It looks like we can split it into two bits. We call this the principal part, and we call this like the other bit. So, and this is just, we can kind of rephrase this as a power series in 1 over z. So, and the key thing to note is that this is a power series of 1 over z, and power series are all holomorphic functions. So we can write that the function that is that power series as just a function g, and g is a really nice function because the domain, the Laurent series converges no matter how close I get to 0, which means it converges. Which means that this bit converges no matter how big 1 over z gets, which means the power series converges no matter how big the argument gets, which means that the power series converges on the entire complex plane, which means g is an entire function. and H is a power series at 0. So H is holomorphic at 0. So I've reduced studying singularities into the study of a bit which behaves really nicely at 0, and what an entire function looks like. And as z gets pretty close to 0, one of us gets pretty close to infinity. And so studying what happens at singularities is really just studying what happens to an entire function as I go to infinity. Okay, so this then motivates our classification of singularities. Studying singularities is all about studying limiting behaviour as we go to infinity. And so we want to classify functions by g. And we want to classify g according to how it behaves as its input goes to infinity. And the three natural cases are that g has a finite limit, i.e. g constant, g has an infinite limit, i.e. g polynomial, and g doesn't have a limit, i.e. g other. I'm not at the moment proving why this classification works, but this turns out to capture the different structure as its input goes to infinity. So let's talk a little bit briefly about what's going on in each of these cases and how to think about them. So case 1, removing. So in this case, the weird part, g, is constant, which means that my function is just a power series. And power series are holomorphic. So kind of my function is defined at 0, and it is holomorphic at 0. I've just kind of forgotten about it. So this is kind of the boring trivial case, which we know must happen, because if we take a holomorphic function and forget it's defined to the point, we can just redefine it at that point. The main thing to take from this case is that if a function is holomorphic at all but a single point, and it's continuous at that point, then it's also holomorphic at that point. And what this means is that being holomorphic is such a strong condition that you can't just stop being holomorphic at a single point without something bigger breaking. On the topic of things breaking, we're going to move on to case 2. So, case 2, this is actually case 3, because case 2 is the interesting case, so I want to do that last. So this is essential singularities. This bit. And so the motivating example here is something like e to the 1 over z. So, because the power, if we write this as a power series, it has infinitely many terms. I'm not going to talk too much about essential singularities because they're hard and messy, but I think the main thing to keep in mind with essential singularities is, so first off, there is no meaningful way to define them at the singularity. I cannot define at the singularity. And when you can't define something at the singularity, stuff breaks in really dramatic ways. So a theorem which I'll prove later is Singularities-Why. What this says is that if I take any kind of really tiny disk centered around 0, or wherever my singularity is, the image of that disk is always dense in the complex plane. And this is like really weird. Like, I take a tiny disk and the output just gets scattered across the entire complex plane. And kind of intuitively, the reason this is true is that an essential singularity is where I've broken what it means to be holomorphic at a single point. And that's such a dramatic thing to do that it just wildly changes my function. Or put it another way, studying what happens locally at a singularity is the same as studying what happens to entire functions as I go to infinity. And so Singularities-Why is really saying that if I have a function which is not a polynomial and not constant, defined on the entire convex plane, and I look at what happens as I go to infinity, then the image is dense in the convex plane. So, or the image outside of a certain disk is always going to be dense. And I'm going to try and later give a much nicer and more elegant proof of this. So the final case is poles. And I think poles are the case where I have the most interesting things to say, because poles are where locally, near my singularity, things look like a polynomial. And polynomials are kind of the lovely special case of holomorphic functions. Polynomials are really nice. And it just so happens that poles are also really, really nice things to study. For example, most basic example of poles is something like 1 over z, like a rational function. Some kind of nice thing with a denominator that can sometimes go to 0. And okay, so first let's think about how we can study poles. There are 3 useful formulations. The first is we repeat our idea of breaking a function into principal parts, but now we can do it at every point. So I say f of z is a polynomial in 1 over z, because now my principal part's a polynomial, so I'm going to call it p, plus something that's holomorphic at 0. And if it has poles elsewhere, I can repeat the same analysis on those other poles. So I kind of keep breaking down the remaining bits into a polynomial in 1 over z minus something, and something that's now that now has 1 fewer pole. So I can just do this repeatedly, and I get that f of z is now the sum of some polynomials plus something that is holomorphic in its entire domain. And this is often a really useful tool. The second approach is, okay, so f of z is a Laurent series, and its principal part is a polynomial, so it has finitely many terms. And what this means is that it looks like C some constant over z to the n plus some constant over z to the n minus 1, and so on. And a natural thing to do when we have a power series is to try and translate things. And this is exactly the same. I just translate things to the right. And translation is then multiplied by z to the n. So if I multiply by z to the n, I now have just a normal power series. And this is a holomorphic function. And so I can rewrite this as f of z is h of z over z to the n. And I can kind of think about this as poles are just zeros of holomorphic functions, but they have negative order. Or, to put another way, a zero is one way to think about a function with roots of order k is that locally the function looks like z to the k. At a pole, the function locally looks like 1 over z to the n. So I can think of this as a 0 of order minus n. And that's why oftentimes you'll see formulas which involve orders of zeros minus orders of poles. And this is interesting because when z gets really close to 0, this also has the condition that h of 0 is not equal to 0 because of how we define, because I'm just looking at the first non-zero term of my power series. And this is important because when z gets really close to 0, h of z just tends to some limit, h of 0, while the denominator goes off to 0, which means that the function goes off to infinity. And this gives me the final formulation, that f of z goes off to infinity as z goes to 0. And this is going to turn out to be one of the key ways to think about poles, because what's really going on with a pole is that it is a well-defined function. I'm just looking at the wrong surface. And the way to define a function of a pole is to invent a new point called infinity, and say that my function is equal to that, the pole. And I'm going to study that in the next chapter. But first, I just want to recap everything we've just done. So, first off, we proved general Cauchy's theorem. This is really just using convex Cauchy several times. All we did was prove the topological fact that any path deformation can be done inside finitely many disks. I then proved that Laurent series work. This was pretty much the same proof of Cauchy's integral formula, but rather than the integral around the circle vanishing, is equal to the integral around a much smaller circle. And I analysed the integral in two circles differently. This gives me a tool to study singularities, which is what I really care about. And there are three, and the way to study a singularity is by observing that locally it looks like the negative bit of the Laurent series, which looks like an entire function as z goes to infinity. And so the way to classify singularities is motivated by the way of classifying entire functions by how they behave as you go to infinity. Constant ones give removable singularities, where I've just forgotten that it's holomorphic. Polynomials give poles that are really nice in ways that I haven't probably talked about yet, but I'm about to talk about. And essential singularities are just saying, essential singularities are kind of the weird case, where something just isn't defined. Yeah?
Sorry to be pedantic, but on that last line you wrote, is that z goes to infinity? I wasn't quite listening when you said
z is the input to my function. So z goes to 0. For example, if f of z is 1 over z, as z goes to 0, 1 over z goes to infinity. That's all this line is saying. Okay, so now I'm going to move on to chapter 5, where I'm going to elaborate on what I just said about how to think about poles. So chapter 5 is, I think, the cool bit of this talk. And it's all about looking at the Riemann sphere. So and the motivating kind of question or idea for this section is I want to study what's happening at a pole by moving from the complex plane to a different surface, the Riemann sphere. So hopefully people have seen the Riemann sphere before in groups or geometry. The Riemann sphere is, you take the complex plane, I then put a sphere along the unit circle, I then look at the top of the sphere, and we've started a new chapter, you've got great timing actually. I can now project from the top of, I can now project the complex plane onto this sphere and back by just taking a stereographic map, where I take the top of the sphere, I draw a line through the sphere onto the complex plane, and I identify these 2 points. Is there something people are familiar with, like they've seen before? Cool. So,
certain methods as well.
just in methods.
Complex methods.
Ah, cool. Yeah. So
Why groups this year didn't do it?
well, so this turns out to be a really important and really insightful way of studying how poles work, because the complex sphere, which I'm going to write as C infinity, looks like the complex plane, but I've now got this magic extra point at the top, the point I use to project. And I'm going to label that point as infinity. And the way to think about poles is just, the image of a pole is not the complex plane. The image of the pole is C infinity, and poles are just points that map onto infinity. So why is this lens a useful lens? Let's take, for example, my function f of z equals 1 over z. So as z gets really close to 0, 1 over z gets really, really big. And as a point gets really, really big, it gets really far away from the origin, which means when I project it onto the sphere, I get really close to infinity. What this means is that if I define f of 0 to be infinity, my function is continuous at 0, i.e. it's continuous at the point whose image is infinity. And we've already studied functions that are holomorphic everywhere but a point, and continuous at that point. Those are removable singularities. So via this lens, a pole is just a removable singularity whose image is infinity. So in what follows, I'm not going to be fully rigorous, because dealing with the Riemann sphere rigorously is kind of hard and messy, and I don't think it's a good use of our time. If you want rigor, go to third year Riemann surfaces. But just to kind of give a starting point for anyone who does want to talk about rigor, just give a starting point for anyone who does want to talk about rigor. We can study the Riemann sphere by saying, I'm going to define, analogously to how we study surfaces in geometry, I'm going to define an atlas of charts on this. Everything apart from infinity, the top point, I'm going to study by just the identity map. I relate it to the complex plane. And everything but 0, I'm going to study with the map z to 1 over z. Because this maps everything but 0 onto the complex plane. And everything that follows, that's how you formalize it, but I'm not going to talk about that. So now I want to try and motivate why the Riemann sphere is kind of an interesting surface, and why it was worth defining. So first off, functions with poles are now defined everywhere. A pole is no longer a point that's weird and broken. A pole is just mapping to the top of the sphere. The second reason to care is that we often want to do things like take 1 over a holomorphic function, and normally we have to care about weird things, like what if the function on the bottom is 0? But we don't have to care about that here, because the function 1 over z is defined on the entire sphere. It just means rotate by 180 degrees, because these points 1 and minus 1 map to themselves. 0 maps to infinity, and then kind of everything along this circle through 0 and infinity just kind of map to each other. And this is like a nice and simple geometric transformation. And this means that we're always able to do things like take 1 over a holomorphic function, as long as we're looking at the surface. And the final reason we care about it is kind of more subtle. So the topology of the Riemann sphere is different to the topology of the complex plane. We've added in an extra point. And for those of you who are paying attention in Mess and Top, this is an example of a one-point compactification. I've added in a new point, infinity, and I've gone from having like this infinite plane to having a compact space, a sphere. And it turns out the things that really constrain a function's behavior are the topology of the domain. This is why studying functions that are holomorphic on disks, these are much nicer than functions that are holomorphic at a disk missing a point. Without the point, we get Taylor series. With the point, we get Laurent series. And Laurent series are much messier. An analogous thing holds here. We've added in an extra point, and this is constraining. And so functions that are defined from C infinity to itself are much more constrained than functions from C to C. And the reason we care about this when we're studying holomorphic functions is that we can translate, if a function from C to C infinity has a limit as z goes to infinity, we can extend it to the complex sphere. You just say that infinity maps to that limit. E.g., if f of z is, I don't know, the z squared, then as z goes to infinity, f of z goes to infinity as well. So I can extend this to a function of the complex sphere, where I can extend this to a function of the complex sphere to itself, where infinity maps to infinity. And this gives me a tool to study limiting behavior of holomorphic functions. If, as z goes to infinity, f of z tends to some limit, I can extend it to the complex sphere. And the complex sphere is compact, so functions from it to itself are much more constrained. And this constrains functions from C to C, this constrains functions on C if I understand their limiting behavior. That was quite abstract, so I want to try and give some examples about and kind of elaborate on why this is so cool. So, first off, for people comfortable with like compact and what compact means, cool. I'll want to find that. So, the first theorem I want to prove to illustrate my point about how constraining being on C infinity is that all functions from C infinity to itself are surjective or constant. Please note that this chapter I'm kind of going quite far beyond what the complex analysis course actually tells you, but I think that this is all really cool and kind of the lens by which much of the second year course makes sense, and so I think it's worthwhile. So this is like a really weird and powerful theorem, and kind of at first glance doesn't even seem true. Like, if I have any function from the sphere to itself, the function is either constant or the image is the entire sphere. Like, I hope this seems a bit intuitively weird to people, but it turns out this just follows naturally from the topological properties of the sphere. So, first off, the sphere is compact, which means that and continuous functions preserve compactness. So the image, f of C infinity, is compact, which implies that it is closed. And I'm now about to show that the image is also open. And if the image is both closed and open, then we're done, because the only sets that are both closed and open are the entire space, or the empty set. And, okay, so why is it open? Here I'm going to use a fact from later in the talk called the open mapping theorem. The open mapping theorem states if f is holomorphic, then it is constant or preserves open sets. The reason this is true is that if you have a holomorphic function, locally it looks like a power series, and locally power series are dominated by their like leading term, i.e. the term with the lowest coefficient, lowest exponent, and polynomial and things which look and z to the k preserves open sets. Like this, yeah, and so this means that my function is either constant or it preserves open sets. And C infinity is open. So the image of C infinity is open. And that's what we wanted. So this result is kind of almost trivial given the setup. And so we're done. And this might seem like a bit of a, I think it might be hard to see why the result is so cool at first glance, but we can get one really cool consequence immediately from this: the fundamentals of theorem of algebra. Because if we have a polynomial, like f of z equals z to the n plus some other stuff, then as z goes to infinity, f of z goes to infinity, which means this is a function. I can extend this to be a function from C infinity to C infinity, where f of infinity is infinity. And, yeah?
Sorry, did you write constant or continuous? That theorem f is subjective and...
surjective, f is surjective or constant.
Is that
Sorry.
is that if it's continuous or if it's holomorphic?
Which one? If it's holomorphic. Sorry.
If it's holomorphic.
Everything that follows, we're going to assume functions are holomorphic because this is basically a talk about why holomorphic functions are nice. Yeah, so the fundamental theorem of algebra just follows from this. Polynomials are functions from the complex sphere to itself, so they are constant or surjective, which means that any non-constant polynomial is surjective. It maps something to 0. It's not infinity because infinity goes to itself, and so the thing that goes to 0 lies on the complex plane, so it has a root. And so the fundamental theorem of algebra is true. Like, this is really cool. And ultimately, this is a bit limited in how it lets us study the limiting behaviour of functions. So I don't think what I've said is probably live up to the hype. Let's prove the second theorem, which I think is much more exciting. Theorem. F from C infinity to itself is rational. I.e., the only functions from the complex sphere to itself are rational functions. And this should seem really weird and unintuitive. But it turns out that this isn't actually that hard to prove. The core idea of what follows is we know that the things that map to infinity look weird and interesting because they're poles. And we know how to study functions with poles. You study functions with poles by pulling out principal parts as polynomials and having an entire bit left over. And the principal parts look like rational functions, and we're going to show that the bit that's left over must be constant. So let's do this. So first off, Willog, I can assume f of infinity is not equal to infinity. This is just like a kind of trivial step I need so I can study things that map to infinity. If f of infinity is equal to infinity, I can just look at 1 over f instead, because if 1 over f is rational, so is f. And this means that the pre-image of infinity is are just poles. And the pre-image, and I can also tell that there are going to be finitely many of them. The reason this is true is, so finitely many poles. The reason this is true is that things that map to poles are zeros of 1 over f. And 1 over f is kind of holomorphic almost everywhere, and so its zeros are isolated, which means that there are isolated sets on the complex sphere. And they're also closed because if you have a sequence of points that map to 0, their limit also maps to 0. And the only closed and isolated sets on a compact set are finite. Have people seen this before, or people like a proof? Do I raise your hand on proof?
No proof, but maybe a bit more explanation.
Sure. So the reason there are finitely many poles is that a pole of f is a 0, 1 over f. Zeros are isolated, and isolated points, and these are isolated points on a compact set because they're on the complex sphere. And if there were infinitely many of them, I could take a sequence, and then that sequence would have a convergent subsequence, and so the set wouldn't have been isolated in the first place. So there are finite many poles. And this means that f of z equals a finite sum of polynomials plus some h which doesn't have any poles. And i.e. h is an entire function. And we know that f of f was defined to infinity, i.e. f of infinity is like some finite thing. And this is also the limit of f as its input goes to infinity. And each polynomial is each polynomial has some kind of constant limits as z goes to infinity, because 1 over z minus a goes to 0. Which means that h also has some constant, has some finite limits as z goes to infinity. Which means h, it can be defined as a function from c infinity to itself. And we know from this that all such things as surjective or constant. But all of the work we've done so far has made it so that h doesn't map anything to infinity. It has no poles, because we've removed every pole. And so h must be constant. And so we've just shown that our function, which was anything from the complex sphere to itself, is the sum of some polynomials of 1 over z, so rational things, plus a constant. So it's rational. Did that make sense to people? Cool. So this is a really powerful theorem. And to demonstrate this, we're going to get a few corollaries of this, which are about limiting behaviour of functions. So first off, we get Liouville's theorem basically instantly. So Liouville's is the study of holomorphic functions. Liouville's is the study of bounded functions that are entire. And if f bounded, then f of z over z goes to 0 as z goes to infinity. Because the numerator is bounded, the denominator is unbounded, so it limits to 0. And having a limit as you go to infinity is what it means to be like extendable to the complex sphere. So f of z over z by this theorem is rational. And so f of z is rational because a rational function times z is still rational. And the only rational functions that are holomorphic on the entire convex plane, i.e. defined on the entire convex plane, are polynomials. And the only bounded polynomials are constant functions. So Liouville's is just a special case of this really powerful theorem about the complex sphere. And so one of the interesting things you get from Liouville's, as I talked about last time, is that Liouville's is really saying that the image of every holomorphic function is dense. Because if it isn't dense, then you can take 1 over f of z minus a point in the region that it doesn't get to, and show that's bounded. The complex sphere makes this seem like much less of a clever trick, much more of a really natural thing to do. Because being bounded just says the image of my function never goes near infinity. And this is the same as saying the image is not dense, because it never goes near infinity. And if the image is not dense near some other point, like say 1, then I can just rotate or somehow transform the sphere so 1 maps to infinity. Like part of the beauty of studying the complex sphere is that infinity is not a special point. Infinity behaves the same as everything else. And you can just rotate the sphere to make this clear. And that's why Liouville's kind of immediately implies the image is dense. We're just studying this kind of notable, interesting special case of being dense, where one of the points inside the region you don't get to is infinity. Or to take another example, let's suppose f of z is less than z to the k as z goes to infinity. Or f is kind of bounded by some polynomial. This is just saying that f of z over z to the k plus 1 limits to 0 as z goes to infinity. Which means it can be extended to the complex sphere, it's rational, so the original thing was rational, it was a polynomial, and so this implies that all things bounded by polynomials are polynomials. And if you think back to example sheet 2, there was a question which was basically just doing clever things to prove things that are really just stemming from this deep fundamental theory. So let's take the most exciting example of this, Kazarati-Weierstrass. Quadratic Weierstrass turns out to just stem really nicely from this core idea. So, first off, let's just kind of link back everything we've done to the question we started out trying to answer. How do functions behave as you get close to singularities? So, we've proven that a function is rational if and only if it can be extended. Which is equivalent to has limit as the input goes to infinity. And you can kind of reverse some of these things. Like, if the function is not rational, then it cannot be extended. And so it does not have a limit. And more importantly, it can't be transformed so that it has a limit. And let's study what quadratic Weierstrass says through this lens. So, the statement of quadratic Weierstrass says f has an essential singularity at 0, implies for all epsilon the image of some tiny disk of radius epsilon centered at 0 is dense in C. And so first off, we're studying behaviour near singularities. And we know our tool for this. We write f of z equals g of 1 over z. So this is holomorphic to 0. As z gets really close to 0, this is continuous, so it doesn't affect density. It just gets really close to 8 of 0. And so we can ignore it. And this is an entire function as z goes to infinity. So what this is really saying is that if g entire, then g of the complex plane minus some disk, like some arbitrarily large disk, is dense in C. Assuming G is an infinite power series, i.e. it's not a polynomial. And this is now language that we can understand using the complex sphere. Because if the image is eventually not dense, then there is some point A where G eventually never gets near it, i.e. for all z bigger than 1 over epsilon, G of z minus A is always bigger than some delta. And we now just apply the same trick we always have. We move this missing point to infinity, we divide by z. So that means that for sufficiently large z, this is bound. For sufficiently large z, 1 over g of z minus a is bounded. So 1 of z times that goes to 0, which means this can now be extended to the complex sphere, which means that this is rational, and we've just applied simple polynomial transformations. So g of z is rational, and g was an entire function. The only entire functions that are rational are polynomials, but g has an infinite power series, contradiction. And kind of this is, like, every time you study limiting behavior of holomorphic functions, this is what's really going on. We have this underlying surface of the complex sphere. We're trying to study this surface, and in everything that follows, or in everything we've just done, we're really answering the question of, can our function be transformed so it can be extended to the complex sphere? So just to recap everything that just happened, this is kind of the natural surface for studying poles, because poles aren't points where the function is not defined. they're just points where we're looking at the wrong surface. They're really things that map to infinity. And this is why they're so nice. This is why we can do things like take 1 over f and get removable singularities. Because taking 1 over f just moves infinity to 0. And this is a much more interesting surface to look at. Or this is a much nicer surface to look at than C, because it's compact. It's got nicer topological properties. And so we get powerful theorems, like that all functions from C infinity to itself are rational, or they're always constant or surjective. And we can translate questions about how functions behave as z goes to infinity into just questions about whether they could be extended to the complex sphere. Just applying symbol transformations to see if we can get them, to see if we can convert weird conditions to be conditions about having a finite limit. The next section is basically completely different to this, so now being excellent time for people have any questions. Yeah?
So for this discussion, you basically identified all the directions that you can go out towards with the one point at infinity. Is there any time you actually have to be very careful when doing this? Is there a simple reason why you can just kind of go, ooh, they're all the same point?
So I guess the kind of reason this works is that the way we formally study the complex sphere is by saying we study the point infinity by taking 1 over z nearby. And if we take 1 over z, it doesn't matter what direction we've gone in. We're going to get really close to 0 from all directions. And all of the proofs you do from Riemann surfaces are just kind of using that to study it. But I don't really want to go into details because it's messy and not that interesting. Cool. Any more questions, or should I move on to chapter 6? So, chapter 6 is on the kind of final section of the course. So, I'm going to call it topology intersecting with analysis. But what it means is I'm just studying things like winding numbers, which are topological ideas, which arise naturally in analysis. And we then get loads of really nice results from this. So the first kind of key thing is that winding numbers are something that naturally arise from looking at contour integration. So the winding number of a curve is kind of a fairly simple idea. We have some points, we take a curve that winds around it, and we just count the number of winds. And this is kind of a very topological idea. Like, it doesn't change as we move our curve around or move our point around. It only changes when, like, the point crosses the curve or they meet. And in general, whenever I say something is like a topological idea, or has a topological intuition, what I really mean is that we can think about it in terms of like making changes smoothly and deforming things, and things only change when something dramatic happens. So, first off, so we get a really nice formula that the winding number of a curve is 1 over z minus a. The reason this happens is, well, there are kind of many reasons this happens. My favorite relies on something I explained in my first talk, the idea that the kind of natural surface to think about integrating 1 over z on is kind of log spiral, like a Riemann surface where you have infinitely many sheets of the complex plane glued together, and the winding number of a curve, when you lift it to this spiral, gives you the number of sheets you go up or the number of sheets you go down. And so the integral of that, so the integral along the curve on my kind of natural log spiral surface is just the amount I've gone up or the amount I've gone down. If you haven't been to that talk, you know what I'm talking about. Another way to think about it is just that taking the integral of 1 over z is a way of constructing an antiderivative of 1 over z. So you construct a log, and this is going to be a continuous branch of log. And if we write a point on the curve using polar coordinates, like r theta I theta, taking log of this is log of r, which is boring, plus I theta. So constructing a log is really a way to kind of study how the angle changes as we move around our curve. And winding around this point is like saying my angle goes up. If I wind fully around a point, my angle has gone up by 2 pi. I don't notice this because the angle is inside the exponent. And so when I'm back to where I started, I can't tell that I've gone around the origin. But log is a way to kind of continuously keep track of the angle as it changes. And so it notices these things. In general, kind of understanding why winding number arises from doing integrals, while like good and fun, isn't important here. The important thing is that winding number is a kind of fuzzy topological idea. I can kind of think about it really nicely, visualize it, and small changes don't matter. But these ideas are really hard to formalize. And on this side, I've got a kind of purely analytical statements. Like, if we follow the course all the way from analysis 1 up to now, we've kind of fully, rigorously, and formally defined all of this. I know exactly how it works. I can deal with it in kind of perfectly well-defined and rigorous ways. And so this is a tool that I can use and formalize and understand. And so the kind of power of this link is I can take ideas that are fuzzy, I can visualize and feel obvious to me but are hard to formalize, and study them with rigorous, well-defined tools. And in everything that follows, we're going to get some kind of obvious and intuitive but hard to prove results, and prove them by linking them to tools for analysis. So let's take some simple examples just using the idea of winding number. So the first thing to note is a kind of fact that I'm going to use a lot, which is that if I have the integral of a continuous function of a, then this entire thing is a continuous function of a. The reason this is true is that I'm iterating along the image of a curve. This is the image of the unit interval, which is compact, and so the image is compact. And a continuous function on a compact set is uniformly continuous. So, and we know from analysis 2 that the integral of a uniformly continuous function is a continuous function. And the reason I care about this is it means that winding number is a continuous function of A. I.e., if I look at kind of any region in here where I don't cross the curve, winding number must be constant in that region. This shouldn't be like a kind of a big wow moment. Like, I think that's quite obvious, but I wouldn't have known how to formalize it before I started doing this stuff. And this is an example of how studying, using analytical tools and understanding how continuous functions work can be really useful and insightful. Or take another example. If I go outside the curve, the winding number is 0. This, again, feels kind of obvious. But one way to formalize this intuition is to observe that I'm taking the integral round a kind of bounded length curve of something that looks like 1 over z. So if I go really, really far away, this is small, while the length of gamma remains bounded, which means that the kind of total thing is bounded. And this means that the kind of total thing limits to 0 as I get really far away. The winding number is an integer. And the only integer that's arbitrarily close to 0 is 0. Which means that the winding number across this entire region outside the curve must be 0. And what I said is an important fact, I should write it down. winding number lives inside the integers, and so because the winding number lives inside the integers, any continuous function whose output is a winding number must be constant, because the only continuous functions on the integers are constant. So now let's kind of actually do some more interesting things with these ideas. So the first thing I'm going to do is the argument principle. So the argument principle says, if I've got some closed curve gamma, which kind of only goes around once, like say, let's just make gamma a big circle. Then I've got some like zeros, z1 and z2, and some poles, p1 and p2. Then of my function f, then the winding number of f of my curve around 0 is the sum of the order of the zeros minus the sum of the order of the poles. So let's, so first off, I just want to kind of emphasize how weird and interesting and important this result is. This is kind of purely an algebraic statement. Like, this is just a statement of what does my function look like? What are the zeros like? Sorry, do you have a question? Cool. What does my function f look like? What do the poles look like? Essentially just, like, this is a thing that I cared about long before I got to complex analysis, if you ignore this part. And this is a purely topological statement. This is a statement about winding numbers of curves. And I can understand this side using topological intuitions, like kind of small deformations will not change this because it's continuous on the small changes. And this side is like really interesting and useful because this is something I care about quite a lot. For example, I can tell you things like solutions to equations by translating my function so that those solutions are just zip roots or zeros. So in everything that follows, I'm going to use topological ideas to say that this side doesn't change. And so I get that the thing I actually care about doesn't change. So first, I want to try and give some intuition for why this result is true. I'm assuming people have seen the algebraic proof in lectures. So people are hopefully willing to accept that this is true. But let's think about why this is true. So first off, let's kind of study the simple case, where there's only a single zero or a single pole inside my circle. Like I've got a really tiny circle. So f of z looks like z minus a to the k, if it's a zero of order k. And so, and kind of intuitively, if I take a tiny circle and I take it to the power of k, I now get a circle that winds around k times. So here the result is true. And the same is true if instead it looks like z minus a to the minus k. Because here I'm mapping a plus e to the plus like tiny thing times e to the I theta to this. And here, so the k is the speed I go around the circle. The minus sign means I go backwards. So I've gone from going around a circle once to going around the other way k times. And so that's why the winding number is minus k. And if I kind of expand out this circle, the winding number shouldn't change until I hit something else interesting. Because as I kind of smoothly deform this curve, the winding number is going to change continuously. But it's an integer, and integers can't change continuously. They can only stay the same. So if I just make it a bigger circle, this should remain the same. And so if I look at all of these, I should just be able to take circles around them, and on each circle the winding number looks like the thing I care about. So the next question is, what happens when two circles merge, i.e. they meet? So let's orient them, and let's look at these two. So now I can, so if I were to go around this circle and then go around this circle, that would be the same as, that would give me the kind of winding number I want. It would be minus the order of P1 plus the order of Z2, because I would wind round this many times and then wind round this many times, they'd add together. And if I just stick these curves together, what I get is a curve that looks like this, and now I can just keep deforming. I don't have to stick at this meeting point. I can get a curve that looks like this. And now I meet something else, I keep merging until I get the entire thing round. So really the argument principle is just following, because locally stuff looks like polynomials, and polynomials are nice. And I can deform things without changing until something interesting happens. And when something interesting happens, I can glue the loops together, another topological idea, and this is the same as doing all the winds from one and then doing all the winds from the other. And that's why this topological idea of the winding number gives me the sum of the orders. Did that all make sense to people? Cool. So I can now use this to do really cool and interesting things. So let's kind of think about a specific example, and let's try and intuit what results might be true from this. I want to study what f of z equals z squared looks like on a circle around 0. So this function has a repeated root of 0. And if I, let's say rather than looking at solutions for f of z equals 0, I will look at solutions to f of z equals epsilon. Now, there's going to be two solutions, root epsilon and minus root epsilon. But what's interesting is that as I kind of smoothly vary epsilon, the solutions to this equation kind of just move outwards following some nice trajectory. And the only weirdness is at the start when they were at 0, but really that was just saying that I have a repeated root at 0, and repeated roots are like having multiple roots on top of each other. And so this motivates the idea that if I have a root of a function, and I want to study solutions to f of z equals epsilon, like things that map close to 0, then there are going to be k of those, where k is the order of the root. And this happens because locally my function looks like z to the k, because it's a power series, and the order is the exponent of the leading term. And z to the k behaves like this really nicely, which we can prove just algebraically. And this is a kind of topological intuition. Small changes shouldn't make any difference. And that's why this amazing tool of the argument principle is going to be useful. So now let's actually do it. So this is the local degree theorem. And the local degree theorem says that if I have a 0 of order k at A, then let's see, for some r greater than 0 and some epsilon greater than 0, then in some like small disk around A, the image contains exactly k solution, k things, exactly k bits of that map to epsilon image, i.e. for all w close to 0 in some disk, there are exactly k solutions to f of z equals w. And this just kind of immediately follows. So we want to study solutions to an equation. And solutions to an equation can also be thought of as roots of f of z minus w, which is the same as the winding number of f of gamma around w. And we can define this as a function of g, and this is just an integral, so it's continuous in w. At 0, it's equal to k, because if we take a really tiny circle, the only zero pole we're going to get is a. And so if we pick a really tiny circle, this is always equal to k. The only other weirdness would be having repeated roots, but again, we can just pick a tiny circle so this doesn't happen. Because repeated roots are the same as zeros of the derivative, but the derivative is holomorphic, and so we can just choose a really tiny disk so that the derivative isn't 0. And so this gets us another fairly kind of intuitive result called the open mapping theorem, which I mentioned earlier. It says that holomorphic functions preserve open sets. And the reason this happens again just follows from here. A kind of consequence of the same that there are exactly k solutions to f of z equals w is that there is like at least one solution, i.e. d of 0 epsilon lies within the image of my function. And there's nothing special about 0. If I have any holomorphic function, I can just translate it to 0 and apply these results. So what this is really telling me is that for all z in my domain, there is some disk lying in the image. And so the image is open at f of z for all things inside the image, i.e. the image is open. And this, again, is a very intuitive result because things locally look like z to the k. The point of using these linking topological ideas with algebraic ideas is it gave us a way to actually formalize this fuzzy intuition. By formalizing the fact that we didn't change things that much, as we're studying a continuous function which has constant output, which has integer output, and so that function is constant. Did that all make sense to people? Cool. The second consequence is Rouche's theorem, which I think, again, is quite an intuitive result, but hard to prove. So Rouche's theorem says if I've got two functions, f and g holomorphic, and I've got some circle gamma, or some closed curve gamma, then if the size of f is greater than the size of g on gamma, f and f plus g have same number of roots, counting multiplicity inside gamma. So let's try and unpack what this means and why it's intuitive. we start with some function f, and we're studying its roots inside some closed curve. We then take the function f plus g, which is close to f in some sense. This condition is just formalizing the idea that f plus g is close to f. Like, their difference is not big enough to matter. And so this is saying if we don't change f by that much, we can't change the number of roots. Did that make sense? And we can now formalize this. The proof that follows is completely different to the proof of lectures. So the proof of lectures is terrible, and the proof is way more intuitive. Hopefully you agree. So, our intuition is that we're not changing f by much, so we shouldn't change the number of roots. And the point of the argument principle is that we can formalize ideas like the number of roots don't change that much by using like continuity arguments. So let's just do that. I'm going to define a kind of family of functions. H lambda as the function f plus lambda g, where lambda is just a real number between 0 and 1. The point of this is that I can think of h lambda as kind of a path from f to f plus g in the space of functions. And in what follows, I'm just going to show that the number of roots is constant along this path, or continuous along this path, and so it is constant. And so we know from the argument principle that the number of roots is this winding number, h lambda of gamma. And this is equal to the integral of 1 over z lambdas. And I want this to be continuous lambda, so I need to kind of unpack this a little to actually deal with lambda in a kind of nice way. And so I substitute w equals h lambda of z, and this means, z equals h lambda of w. And so now I just have an integral around a closed curve of the derivative of h lambda over h lambda. And I can unpack this. This is this thing. And kind of, this is all just algebra. The important thing is, the thing that I care about, the number of roots of h lambda, is this integral. And this integral is a continuous function of lambda, so long as the denominator is never 0, because the denominator being 0 would be the equivalent of kind of, as I deform this curve, things cross the origin. And if you look back to our original condition, which means f doesn't change that much, this is kind of exactly what you need to show that this thing is never 0. Because the absolute value of f plus lambda g is at least f minus lambda times g, which is at least f minus g, which you know is a greater than 0 everywhere along this curve. And so this is a defined function, and it's continuous in lambda. So it's uniformly continuous, and so the integral is continuous in lambda, which means that the number of roots of h lambda is a continuous function, and so we're done. And like, this is all Rouche's theorem is saying. Hopefully you agree this is better than the proof they give in lectures. And cool. So, and just a brief note on, sorry, no question?
I'm just wondering, if that's not, if it's not the case that the absolute value of f is always greater than the absolute value of g, but you still have that the absolute value of g is less than a fixed constant times the absolute value of f, could you just repeatedly add small fractions of g and
So
get that f plus g also?
The problem with that approach is that if, for example, f of z equals z, g of z equals minus z, then this statement is kind of silly and false. Because f plus g is 0, the number of roots of 0 inside a circle is kind of a nonsensical idea. And the point of this condition is just to prevent silly stuff like that. You could strengthen it. Like, all you really need is that f plus a real multiple of g is never 0, which is like a weaker statement than this, but in kind of all of the actual applications, you want something easy to prove, and this is easy to prove. So, for example, you get the fundamental theorem of algebra as a consequence of this, because if you pick a really big circle, then polynomials are just a kind of small fudge of their leading term. The leading term has like the degree number of roots inside, and so the small fudge has a degree number of roots inside. This is a kind of really intuitive proof, and the value of Rouche's is that you can formalize stuff like this. So let's just kind of recap what we've done. So topological ideas arise naturally within complex analysis, mainly because integrals turn out to be a way of studying like the topology of our space, the holes of our space, and because we're in 2D, studying holes ends up turning out to study winding numbers. The number of times a curve winds around a hole. This is most of interest to us because we can link this to an algebraic fact via the argument principle, a fact about roots and holes, which is a fact about kind of solutions to equations, a thing we really care about. And this is insightful because you've linked topological ideas, fuzzy intuitions about small changes, to this kind of clear, concrete algebraic thing we really care about. And things like the local degree theorem and open mapping theorem are formalizing the fuzzy intuition that things locally look like z to the k. And Rouche's theorem is formalizing the fuzzy intuition that if you don't change a function by too much, the roots can't change, the number of roots can't change. You need to do something dramatic to change the number of roots. And all of the conditions with Rouche's theorem are just kind of what you need to shape this idea. Are there any questions on that section? Cool. So I don't have much time left, so we're going to go on to the short final section called How to Do Contour Integrals Compositely. Because I know you all came here for some applied maths. Sorry?
How to do contour integrals?
Competently. Because I want to get some vision out of this talk, so learning how to do contour integrals seems like a great excuse to write a chapter. Well, all the way around. But so I'm kind of going to assume, hence in everything that follows, that people are kind of familiar with the idea of contour integration. So I'm going to focus less on the details and try and focus on like the high-level ideas and tricks and kind of how to actually approach an unfamiliar problem using contour integrals. Or rather, how to kind of look at an integral and figure out the right contour to use. Because I think that's kind of the one hard part of contour integration. So on a really high level, the art of finding the right contour is all about putting on a piece of paper the sensible geometric objects like lines and arcs, so that things behave, so that kind of my function behaves nicely on these lines and arcs. I then want to complete them into a closed curve. I use the residue theorem to find the integral around the closed curve. I then have one bit of my contour which is interesting, or kind of like one line where I don't know how to calculate the integral, or maybe two lines where I don't know how to calculate either integral, but I know how to relate them, and I just solve an equation to find the integral I care about. And in everything that follows, the clever ideas are going to be about how to find like other lines and other curves where I can kind of relate them to this core integral that I really care about. So the first aspect of contour integration is how to deal with things that look like this, like functions of cos and sine where the limits are between 0 and 2 pi. This is kind of a trivial special case of contour integration, because if I look at the unit circle, and I sub z equals e to the n theta, these are really easy to deal with, because this is just the integral around the unit circle of f of z plus 1 over z, and z minus 1 over z. So I'm not going to talk about this anymore. Like, just look at if you see limits that look like 0 and 2 pi, or 0 and pi over 2, or 0 and pi, you just want to make it into a thing you can turn into the unit circle, and then you're basically done. So this is kind of the easy intro case. Where things get interesting is where we're looking at line integrals, i.e. integrals from 0 to infinity of something. So the way you deal with this is you have your complex plane, you put a line between like 0 and r, we understand r to infinity, and we want to put on other things on this diagram to make things go to infinity in a sensible way, or so that we can kind of just complete our contour. And the things we want to put down are things that will be nice, where the integral will be nicely related to the integral along this line. And the way we do this is by exploiting the symmetries of the complex plane. So in everything that follows, the key thing to be paying attention to is the symmetry we're using and how to recognize which functions behave nicely under this symmetry. So symmetry 1, rotation. This is how you deal with things that look like things that have lots of z to the n's in them. Like this has a z cubed in there. And the symmetry is w equals lambda z, i.e. a rotation. This is just exploiting the fact that if you have something that looks like z to the n, like z cubed, and you multiply by an nth bridge of unity, then that power is the same. And so this motivates taking the contour, that is a rotation by 2 pi over 3. And if we do that, we then can complete our contour by just taking the circle round. This is going to be nice because kind of circles of arbitrarily big or arbitrarily small radii are almost always nice. And we're now just done, because the integral along here is going to be like x 4 pi I over 3 times my original integral, and this is my original integral. And so the big takeaway here is whenever you see lots of z to the n's around, you rotate. The next symmetry is translation. This is what motivates rectangular contours. So here we're studying more things between minus infinity and infinity, with lots of e to the z's and hyperbolic trig functions around. Like say e to the z over 3 over sec z, or say cosh z. And the key thing to observe here is that when you map w equals z plus 2 pi I, i.e. you translate, hyperbolic trig functions and things that look like e to the z are the same. And the thing on the top isn't quite the same, but it's close enough. And so here, we started with this line, and noting things like hyperbolic trig and e to the z motivated the idea of translate upwards. We now just complete our contour into a rectangle because the bits at the end are far away from the origin, so we hope they go to 0, and we're now done. The final symmetry I want to talk about is kind of the interesting weird case, and it's something that only happens in complex analysis. So really these are what you'll have seen as keyhole contours. But really I want you to think of them as like branch cuts, as symmetries that arise whenever you have a branch cut. So these are to do with integrals like, say, z to the half over 1 plus z squared. We're looking for things that have, we're looking for functions that have branch points, like z to the half, z to the third, log z. And so, wait, did you do keyhole contours in lectures? No, well.
He didn't have enough time, so he gave out a handout.
Do people want to see keyhole contours done properly, or are people cool with that? Raise your hand if you want to see keyhole contours done properly. That's actually enough people that want to do a keyhole contour properly, and then talk about the pretty maths behind it that's really going on. So, okay, we want to do this integral, and so z to the half is not defined on the entire convex plane, so we need to have a branch cut. And the integral, the line we want to look at is like this line, but it turns out to be quite nice to actually take a branch cut along this line, and instead of taking a line along this axis, take a line slightly above this axis and slightly below this axis, wind round into a keyhole here, wind round into a keyhole here. So this breaks my curve into 4 bits: gamma 1, gamma 2, gamma 3, gamma 4. And the kind of reason branch cuts are annoying is that via the kind of simple convex analysis view, it's not defined along this cut, so I can't take a contour around it, which is why I've had to kind of go out of my way to avoid it. But now, because I've avoided the branch cut, this is like a symplecant space that doesn't contain the branch point. So this is all the integral of the closed curve. The singularities are kind of naturally easy to think about. They're plus or minus I. So I know the integral around the entire curve. And now I just want to study the integral of each bit. And this isn't that hard. So the integral of gamma 3 goes to 0 because, as a general rule, as the radius of the curve goes to infinity, if the function inside is bigger, littler of 1 over r, it's going to tend to 0, because integral adds a kind of a linear length factor. Here, the big O is like z to the minus 3 over 2, and so it goes to 0 as z goes to infinity. So like, gamma 3 is boring. Gamma 1 is also boring, because here, I'm looking at the integral around a tiny curve. And so I'm kind of doing the same thing, integration adds a linear factor, but here I want to look at the kind of smallest power terms. So the denominator, 1 is much bigger than z squared. So the denominator looks like 1. The top looks like r to the half times like whatever the square root function gives me. And integration provides me some kind of linear factor. So the integral inside is like littler of 1 over r, like it actually just goes to 0. Integration provides a linear factor of length, and so the entire integral goes to 0. In general, if this isn't true, these are kind of annoying. Sometimes if the integral is exactly 1 over r in either case, then I'm happy. Or I can kind of actually explicitly calculate the integral, and I have a leading constant term, and then everything else goes to 0, and I can just do analysis to it. But you kind of pray those cases don't happen because they're normally messier. And so this bit goes to 0. So the integral around the entire curve is just the integral along gamma 2 plus the integral along gamma 4. And the key thing to observe about keyhole contours is that gamma 2 and gamma 1 are in different directions. They're really close together, and they're on opposite sides of the branch cuts. Another thing to note is that if we're doing this formally, we have 3 parameters: the width of the keyhole, the radius of the small bit, and the radius of the large bit. And so, and in general, in analysis, things are weird when we have 3 different variables and they're all tending to things. But it turns out with keyhole contours, this isn't an issue. So we've studied what happens as r tends to 0, this goes to 0. As big R tends to infinity, this goes to 0. Along these bits, something funky happens. So if we look at z, if we look at like f of z on this side of the branch chart, it kind of tends to something normal, and like this function behaves continuously above, and it behaves continuously below. The weirdness about branch cuts is that depending whether you approach from above or below, you get a different answer. Because on the top, I'm kind of taking the limit of f of z. On the bottom, I'm taking a limit tending to e to the 2 pi I z. And functions which have branch cuts are functions where when you substitute z equals e to the 2 pi I z, things don't give you the same answer. So here, substituting e to the 2 pi I z gets me the negative square root. So what this means is that my integral along the top is the negative of the integral along the bottom. But they go in opposite directions. So I'm actually taking the difference between the integral of kind of normal parts and the integral of e to the 2 pi I z. So this is going to look like minus e to the 2 pi I z 2 e to the 2 pi I z squared. This doesn't matter. This becomes a negative sign, and so this whole thing becomes a plus, and so I just have twice my original integral. And in general, if I'm doing branch cuts right, if I'm doing keyhole contours right, these things should never cancel perfectly. They should just give me a kind of thing very related to my original integral. Does that make sense, people? Cool. And in general, whenever you have a branch cut, you want to do something like this to avoid it. Like, there's a question on the example sheet about log z squared plus 1 over z squared plus 1. One way to deal with that is to say, log z squared plus 1 has a branch cut along here. I want to take in contour that looks like this, so I just avoid the branch cut, go round, go up, and go round. And you deal with the branches of the keyhole by saying it's z versus e to the 2 pi I z. You deal with this by saying it's a small circle, and you hope that this is all just lovely and doesn't matter. But I promised you an explanation of why keyhole contours are really an example of applying symmetry. And it turns out that the branch above and below the branch cut, the line above and below the branch cut are kind of deeply related to each other and deeply symmetric in interesting ways.
Sorry, how do you do log z squared plus 1 over z?
Sorry?
How do you do log z squared over plus 1 over
the idea is you kind of try and do it normally, but then when you try and complete the contour, you have a branch come up here, and you just go around it with a keyhole, and things get a little bit messy, and you need to actually pay attention to your limits and the terms you get out, but it all works. I really don't want to do an example question in immense detail up here. There's also a nicer solution, which I'm also not going to give. So the reason this is just another example of symmetry is that thinking of a keyhole as kind of got a line up here and a line down here, but the function isn't defined along this axis is a mistake. Because we know that branch cuts are really nice. Who's the president?
Sorry?
Who's the president?
Oh, no idea.
We know that as if you kind of move a branch cut around, we've still taken a continuous slice of our function. And so this line is actually defined here. We can just extend this branch of log round. And this line is also defined on this axis. We're just extending this branch of log around from this direction. The interesting weirdness is that when we extend our definitions of log from two different directions, they don't agree. If you were at my first talk and you saw the kind of Riemann surfaces idea, the idea of the log spiral, what we've just done is we've taken our line along one sheet of the surface. We've then gone up one sheet, really close to the axis, gone along the same line on the sheet above, and then wound back round to the sheet below. And this is kind of this is like a really fun, cool example of symmetry you only get in complex analysis, because only with branch cuts do we have these sheets going up one sheet. And obviously if you go up one sheet, you should get something really related to your original function. And that's not really going on with Keeler contour. The symmetry is e to the 2 pi I z. Yeah, and pretty much every contour interval question is spotting one of these three symmetries, or seeing it's the first case. And the final thing I want to close on is why Jordan's lemma is bullshit. So, Jordan's lemma, for people who got understandably bored during the section on complex analysis, says that if I have an integral that looks like this, where on gamma, where gamma is a big semicircle, then this integral tends to 0 as r tends to infinity if lambda is positive. So what this is really saying is that, well, the reason we care about this is I care about integrals along the real axis. I need to complete them into a closed curve, and so I want to be able to complete it. And, okay, sorry, this has the condition of f of z goes to 0 as z goes to infinity. And the reason I care about this is that I want to study the integral of e to the I lambda z times f of z along this axis. Say I want to study the integral of sine z over z. And I split this into things that look like e to the I lambda z divided by z. The reason I'm taking, well, there isn't a reason I'm taking a semicircle. The reason I take something like a semicircle is that e to the I lambda z gets small as the imaginary part of z gets big. So if I head vertically up, it becomes really small, and then I can just complete my contour, and then it only becomes big again when I go down. And the condition, so like kind of on this bit, it's small. The condition f of z goes to 0 tells me that on these remaining bits, it's also small. And the kind of proof of Jordan's lemma is kind of an attempt to glue these two ideas together and show that the integral vanishes on this entire contour. And the kind of hard, icky part of Jordan's lemma is that we're trying to integrate something that looks like e to the I lambda r e to the I theta, and it's just horrible. But we don't actually need to do this. Because the only things that are important were that our contour went up quite fast, and it never went near the origin. And this doesn't uniquely characterize a semicircle. And in fact, if we take a triangular contour up to IR, the proof just works. Because we don't need to take a linear approximation. We have a line. So let's just z equals r times 1 plus t I minus 1. We sub it in. We end up with e to the minus lambda rt plus I times some crap times f of this bit. And we care about the absolute value of this, which means we only care about the absolute value of the inside, and which means we don't care about this stuff. This is bounded, because this goes to 0, because the big R is never gets near the origin. So we can just pull this outside. This is just like small. And And now we're integrating e to the minus lambda RT, the t between 0 and 1, and we can do this. Oh, sorry. This should be r I minus 1 times dt. The I minus 1 bit is just root 2, so this is just like a factor of r. And so this is small times root 2r times like 1 over lambda r minus e to the minus r over lambda r. As r goes to infinity, this tends to 0, because all of this stuff is just constants, and this bit is the leftover term from f. And like, this is all Jordan's lemma is saying. I have absolutely no idea why they use a semicircle. It's horrifying and awful. This works. You don't even need Jordan's lemma. You can just draw a triangular contour and just prove this every time, because it's really quick.
This is equivalent to Jordan's lemma, right?
Yeah, because you can deform the triangles of the semicircle using general Cauchys. It's just so much nicer, and I do not understand why they don't do this in the course. This is almost as bad as that proof of Rouche's theorem. Yeah, I had a few random comments about quantum integrals, but it's a bit late, so I don't have anything to do with that. So just to kind of recap the core idea here. Quantum integration is all about finding simple geometric objects and completing them to a closed curve. And it's all about exploiting symmetry to find nice geometric objects. And there are basically only 3 symmetries you care about. Rotation, look for things that look like z to the n. Translation, look for things that look like e to the z in hyperbolic trig. And branch cut symmetry, which just you're kind of forced to do whenever you have a branch cut. And you just want to have the same line, but from 2 different directions. And the symmetry is represented by each e to the 2 pi I times z. And that's how you do quantum integrals. Any other questions? Any final questions? Cool. In that case, thank you very much for coming. Pleasure for everyone. Yes?
Who's lecturing complex analysis this time?
Cobbler.
I think someone needs to email him.
Someone needs to send him these videos.
Oh, yeah, lots of questions.
When's your vector calculus talk coming, Neil?
Hey, Andy.
You're going to email Hunt, I think, because like.
Sorry.
I mean, I'm going to start at